Okay, class, today we are going for a ride. Today we are going to start talking about redox reactions. My objective for you is that you'd be able to identify elements that go through reduction and oxidation within a chemical reaction along with their respective oxidizing and reducing agents. In saying that, let's dive into these deep and confusing waters that we call redox. So we have used the complex world of dating and marriage to learn about the 5 types of chemical reactions this year. We have used marriage to illustrate synthesis reactions, divorce to illustrate decomposition reactions, dating and cheating on your significant other as single and double replacement reactions, and all your relationships going up in flames with combustion reactions. Today we are going to go farther into types of chemical reactions and introduce to you the concept of redox reactions. Redox reactions occur when electrons are transferred from one substance to another. Redox is short for oxidation reduction reactions. We will go further into those words in a minute, but for now, let's look into the burning of magnesium in air, which is a combustion reaction involving the transfer of electrons. The complete chemical reaction for this is 2Mg solid plus O2 gas yields MgO solid. If we split this up into its ions and produce the net ionic equation, it would read 2MgS plus O2 gas yields 2Mg plus 2 plus 2O minus 2. Our magnesium and oxygen do not have an oxidation number because they are individual elements by themselves, but they come together to form a product in the form of magnesium oxide, or MgO. When they do this, they acquire an oxidation number as shown in this equation. We can see that our magnesium loses 2 electrons, or negatively charged particles, because it goes from a neutral oxidation, 0, to a positive oxidation, while our oxygen goes from a neutral oxidation to a negative oxidation, so it must have gained electrons. Specifically, in this reaction, oxygen gained 2 electrons. So let's track the movement of electrons in another equation. Let's take a single replacement reaction of potassium bromide reacting with chlorine. Our balanced chemical equation should read 2 KBr aqueous plus chlorine, or Cl2 aqueous, yields 2 KCl aqueous plus Br2 aqueous. If we make this into an ionic equation, it would read 2 Br2 minus 1 aqueous plus Cl2 aqueous yields Br2 aqueous plus 2 Cl minus 1 aqueous. We can see that the chlorine went from being neutrally charged, or from being neutral on the reactant side, to being negatively charged on the product side. We can also notice that the opposite is happening to our bromine atom. This tells us that bromine is given an electron over to our chlorine in this equation. Now that we can see the electron transfer throughout an equation, we can talk about the words oxidation and reduction. Oxidation is defined as the complete or partial loss of an electron from reacting substances to products. So if we look back at our net ionic equation for potassium bromide and chlorine reaction, we would see that bromine goes from a negatively charged ion on the reactant side to a neutrally charged particle on the product side. This tells me that bromine is going through oxidation in this reaction. For oxidation to occur, the electrons lost by a substance that is oxidized must be accepted by an atom or ion of another substance. In other words, there must be an accompanying process that involves the gaining of electrons. Reduction is the complete or partial gain of electrons by reacting substances. In other words, a substance will become more negative on our product side than it was on our reactant side. Look at our potassium bromide and chlorine example again. Chlorine goes from being neutrally charged on the reactant side to being negatively charged on the product side. This tells me that chlorine is going through reduction in this reaction. Reduction and oxidation are a pain to remember, and if you don't get them straight, you'll be second-guessing yourself every time you see one of these problems. How I like to remember this concept is using the acronym OIL rig. OIL stands for oxidation is loss of electrons, while RIG stands for reduction is gain of electrons. If we take the synthesis of potassium chloride, the reaction would read as followed. 2K solid plus Cl2 gas yields 2KCl solid. We could state that in this reaction, potassium is oxidized by chlorine, which would be useful because it clearly identifies both substances that are oxidized and the substance that does the oxidizing. The substance that oxidizes another substance by accepting its electrons is called an oxidizing agent. Let's say that one more time. The substance that oxidizes another substance by accepting its electrons is called the oxidizing agent. This term describes the substance that is being reduced. The substance that is being reduced by another substance by losing electrons is called the reducing agent. A reducing agent supplies electrons to a substance being reduced or gaining electrons. The reducing agent is oxidized because it loses electrons. So in the synthesis of potassium chloride, we can say that potassium is oxidized in the reaction because it loses electrons to chlorine, and chlorine is reduced because it gains electrons from potassium. Now, to confuse you even more, chlorine would be the oxidizing agent, while potassium would be our reducing agent. Okay, so I know this is most definitely where the second guessing of your life comes in now. So let's look at this another way, or at least organize it into a table for you. Oxidation is when reactants lose electrons. A reducing agent is one being oxidized and the oxidation number of an atom increases. In the process of X turning into Y, X loses electrons. X is a reducing agent and becomes oxidized, and the oxidation number of X is increased. When reduction happens, on the other hand, reactants gain electrons. So, the oxidizing agent is being reduced, and the oxidation number is decreased. In our X going to Y illustration, Y is going to gain an electron. Y is an oxidizing agent and becomes reduced, and that is because the oxidation number for Y is decreased. The chemistry of oxidation-reduction reactions is not limited to atoms of an element changing to ions or the reverse. In some redox reactions, changes involve molecular substances or polyatomic ions in which atoms are covalently bound to another atom. For example, let's look in the formation of ammonia. N2 gas plus 3H2 gas yields 2NH3 gas. This process involves neither ions nor any obvious transfer of electrons. The reactant and product are formed covalent bonding molecules from compounds. By definition, that means that these molecules are technically sharing electrons. But how is this a redox reaction then? I thought electrons needed to be transferred for a redox to occur. The answer is electronegativity. If we remember back to earlier in the year when we talked about the periodic trends, electronegativity is the ability for an atom to pull an electron towards itself. The more electronegative an atom is, the stronger the pull that atom has on its neighboring electrons. Hydrogen has an electronegativity of 2.2, and nitrogen has an electronegativity of 3.04. Or that means nitrogen is going to be more likely to pull electrons from neighboring atoms than hydrogen will. With this illustration, we can come to a conclusion that the more electronegative an atom is, the more likely it's going to gain electrons or be reduced. On the flip, the less electronegative an atom is, the more likely it's going to lose electrons or become oxidized. This means atoms with a higher electronegativities are oxidizing agents, while lower electronegativities are going to result in reducing agents. For illustration, nitrogen is going to go through a reduction because of its electronegativity state and is more likely to hold or gain electrons. Thus, since it gained electrons, our nitrogen is our oxidizing agent. While hydrogen is our least electronegative atom out of the compound, so it's more likely to go through the process of losing electrons or being oxidized. This means it is our reducing agent. Okay, so if I haven't confused you enough, let's talk about rules for determining oxidation numbers. In order to fully understand these types of redox reactions, you must be able to have a way to determine the oxidation of each element involved in a reaction. Here are the rules for assigning oxidation number. Your first one is that the oxidation number of an uncombined element is always 0. This is an example of like O2 or Na. So any element by itself, not combined with anything else, has an oxidation of 0. Second rule, the oxidation of a monoatomic ion equals the charge of the ion. So calcium plus 2, its oxidation is plus 2, or Br minus 1, its oxidation is minus 1. Third, the oxidation number of the more electronegative atom in a molecule or complex ion is the same as the charge it would have as an ion. So in NH3, nitrogen is our most electronegative and it has an oxidation trend of -3. In the compound NO, oxygen is our most electronegative, so the oxidation of oxygen is -2. Our fourth rule is the oxidation number for anything bound to fluorine is -1. So LiF has an oxidation of -1. Our fifth rule is the oxidation number of oxygen in a compound is always -2, except in peroxide, such as O2 or H2O2, where the oxidation is a -1. So the oxidation of oxygen in NO2 is a -2, while the oxidation of oxygen in H2O2 is only -1. Our sixth rule is the oxidation number for hydrogen is +1 in most compounds, except when it is paired with a metal to form a metal hydride. If in that case, it's going to be a -1. Our seventh rule of oxidation is that the oxidation number of group 1 and 2 metals and aluminum are positive and equal to their number of valence electrons. So potassium would have an oxidation of +1, calcium have an oxidation of +2, and aluminum have an oxidation of +3. Our eighth rule is the sum of the oxidation numbers in a neutral compound is 0. So in calcium bromide, CaBr2, we would have one calcium atom with an oxidation of +2 and two bromine atoms, each containing a -1 oxidation. This would cancel out, giving us a total neutral atom. Finally, the sum of oxidation numbers of an atom in a polyatomic ion is equal to the charge of that ion. So in SO3 we would have 3 -2 charges coming from our oxygen. This gives us a total of -6 oxidation number. In order to get that to a -2 charge, this means our sulfur must have an oxidation of +4. -6 plus +4 equals -2. Okay, that should be enough torture for the day. I hope you were able to keep up with everything today, and I know I threw a lot at you, so take a deep breath, keep up the good work in class, and see you next time.